Swayam Prabha. Digital India. Educated India.
We will discuss some algorithms for running a constant temperature MD simulations. So far all the discussion on MD simulation was in the microcanonical ensemble, where the energy was fixed at a constant value along with number and volume. And we go about solving Newtonian mechanics, which is an energy conserving equation of motion. But in many experimental systems, we see that the temperature is held constant because we might want to observe certain physical process as a function of temperature. So we may conduct experiments at a different temperatures. So if our aim is to measure properties from MD simulations so that we can compare with experiments, so then we also have to devise methods and algorithms by which we can do MD simulations at constant temperatures as well. Now, one way to think about this is, we already talked about equivalence of ensembles. That means I can run a simulation in a NVE system, measure some property, and then find the equivalent values in another ensemble. For example, if there is a property A, I could very well calculate it in a microcanonical ensemble, and then we see that the difference between the same value estimated between NVE ensemble and NVT ensemble is proportional to 1 by n. So one can always run simulation in NVE and then find out the equivalence of the values in another ensemble like constant temperature, which goes as the difference between such ensemble will go as 1 by n. So there is always such a method, but however, we like to look at specific direct algorithms where the temperature is held constant during the simulation itself. So now, before we proceed further, let us look at what we mean by constant energy simulations and constant temperature simulations, and what we mean by that in terms of the phase space and the configurational degrees of freedom. You might recall that when you have an n particle system, there are 6 n dimensions or degrees of freedom that are there in the system, and we can pictorially show it is of such a volume given by this kind of a cubical shape. And then when we fix a particular energy, this basically means the trajectory of the system basically goes around a constant energy surface, which is denoted here by the surface of an ellipse here. Okay, this is only a pictorial representation, where each point in this particular trajectory shown by this yellow curve, you will see that the system's entire microscopic state are mentioned, that is the particle positions and velocity, everything specified at any given point in this any point on that yellow curve. And then the trajectory basically samples the microstates around the surface of this ellipsoids, because we think that the constant surface area, the constant energy is given by the surface area of this ellipse. On the other hand, when we look at NVT ensemble, where the temperature is being held constant, then we know that the system can actually jump from one energy level to another energy level. So here I show different ellipses, each one of them corresponding to different energy states. So you might start with the system, and the system may sample along the surface of this particular energy EC, but then once in a while it also makes transitions to another energy levels and then keeps visiting different kinds of energy levels, so that the energy is fluctuating by keeping the temperature constant. So we would like to always remember that in a microcanonical ensemble, the trajectories basically span the configurational space or the phase space where the energy is constant, whereas in a constant temperature simulations, the system is allowed to transit between different energy levels. So it can make energy transitions and then revisit across a range of energy levels. And this is something is more intuitive for us, because if you think about an experimental system where I want to maintain the temperature constant, what I would do is I take the system and then immerse it in a reservoir, which I call here as a surrounding, which is maintained at a desired temperature. And when we do that, when we couple the system with the surrounding at a constant temperature, any change happening in the system will lead to flow of energy through the walls, through the boundaries of the system across the system and surrounding boundaries. So, there is always energy exchange between the system and surrounding, thereby the system is able to sample different energy states so as to keep the temperature constant. The same phenomena is what we have shown in the phase space, where the energy transitions can happen within the system. So, we keep this in mind, and then we will try to go about MD simulations where the temperature may be held constant. Now, we are going to look at bunch of methods. There are several methods, but for practical reasons we will consider some representative examples which are often used in MD simulations in research as well as in teaching. First, the most simplest thing you can do is we can find what is the instantaneous temperature in the MD simulation, and whenever this temperature is not at the desired temperature that you want to have, what you can always do is you go back and then take the velocities of each particle and then rescale by a certain amount, so that the temperature can be held at the desired level. So, it is like rescaling artificially the particles velocities at every time step. And to find out what is the scaling factor, we can always go back and then find out how we used to measure the temperature, the instantaneous temperature, using the momentum or the particle velocities. So, at any given point of time, at any time t, we measure this instantaneous temperature, and then this temperature may be different from the T set. T set is the desired temperature that we want the system to be at. So, now what we can do is we can take all the velocities and then multiply by a factor of lambda, so that the temperature can be set at the T set temperature. So, now suppose if I multiply all the velocities by a scaling factor of lambda, and then I can find that the T set is given by lambda times Pi, because each of the particles velocities are multiplied by a factor of lambda. So, in the definition of our temperature, there is a factor of lambda comes out, but lambda is a scalar, as a constant. I can take it out, and then I can show that the T set is given by lambda square times the instantaneous temperature at that particular point of time. So, from here we can solve what should be the scaling factor. The scaling factor is given by square root of T set by the instantaneous temperature T. So, this instantaneous temperature can be a function of T, and because of this lambda will also be a function of T. That means, the scaling factor will keep changing depending upon what the instantaneous temperature is. So, the idea here is to measure instantaneous temperature. If at all it deviates from the set temperature, you are going to assign your desired temperature. In fact, this method is basically called isokinetic MD simulations, because by doing this rescaling of velocities, we essentially keep the kinetic energy constant, through which we calculate the temperature, which is also maintained constant at every time step. However, if you look carefully, we will find out that this kind of an isokinetic MD simulation to keep the temperature constant is not strictly a constant temperature simulations. The reason being that if you have a constant temperature simulation, the kinetic energy is allowed to fluctuate. So, you can work it out from statistical mechanics, and we can find that there is a finite fluctuation of kinetic energy in a true constant temperature simulations. However, in isokinetic, by construction, we are keeping the constant kinetic energy. So, there is going to be a little bit of a difference between isokinetic MD simulation and isothermal MD simulations. However, the difference here becomes very small as you go to larger and larger system size. So, because of all this ad hoc way of rescaling the temperature at every time step, and the fact that it can be slightly different from isothermal condition, we only apply these kind of a rescaling methods only during the equilibration step, so that the temperature can be set very quickly. Whereas, when we go to the production run, where we make measurements of velocities, autocorrelation functions, or transport properties, we have to look at some better methods which is more reliable, more accurate. But to start with, this is the simplest way of thinking about resetting temperature, so that you can do you can solve the equation of motion using one of the time difference method, but every time point, before we go to the next time point, we check whether the temperature is at the set temperature or not. If not, then you basically rescale with a factor proportional to the square root of the set temperature divided by the instantaneous temperature. and you can see that at any time if the instantaneous temperature is T set, then the lambda becomes 1. That means you are not really doing any scaling there, and this we say something called a constraint method. This is one of the class of methods known as constraint method, because we are constraining the kinetic energy here. And velocity rescaling is one such example of a constraint method. So now little better way of doing this temperature resetting is to think about this this experimental system where you have a system and this is immersed in a surrounding, and then to maintain the system's temperature constant, the system is exchanging energy with the surrounding. So there is going to be some sort of heat flow across this boundary. So now in this thermostat that I am going to talk about, which is known as the Berenson thermostat, here we assume that the heat transfer is actually proportional to the energy difference, the temperature difference between the system and surrounding. So we think of this as a first order process, and we model the rate at which the temperature changes with respect to time for the system is proportional to the temperature difference between the system and the surrounding. So here we think that the surrounding is at a T set temperature and the system is at temperature T at any point of time T, and then the rate here is given by some inverse of some time constant, and this time constant will tell us how strongly the system is coupled with the surrounding. So in this construction, what we try to say is that we think of the system to be coupled with an external bath or the surrounding, which is maintained at the desired temperature, and this bath or the surrounding, it acts as a source of heat or thermal energy, so that it can supply or remove heat from the system. So now the heat transfer is actually modeled using a simple first order process, and this time constant tau here is something that reflects how strongly the system and surrounding are coupled. And since it is a first order process, you will expect that the time constant tau tells what is the rate at which the temperature is catching up with the T set value, and if you solve this, you will see that the temperature exponentially reaches the desired temperature, and the rate of which is given by the value tau. So now in implementing this Berenson thermostat in MD simulation, the way forward is you do not integrate this equation, but rather write this equation for a very small delta t, where the small delta t is a time step. So the left hand side is given in a difference formula. So we convert the differential formula into a difference formula. So where this dt is given by delta capital T, and the small delta t, that is a time, is given by small delta t, and the right hand side term remains as such. So now if you look at this delta t, we can show that we can always scale the particle velocities by a factor of lambda, such a way that this delta t can be taken care of. So we just now saw in the previous velocity rescaling method that this scaling factor lambda has to be proportional to T set by T, reset the temperature in one step. But in Berenson's thermostat, we are not going to do this resetting in single step itself, so that the temperature is maintained at T set, but rather we are going to do it very slowly and gradually, and the rate at which we are going to do is given by this time constant tau. So now we go to this scaling factor lambda, and then if I calculate lambda square minus 1 from this expression, I see that this becomes T set minus T set by T of T minus 1, and then if I solve this, I can show that this becomes delta T by T of T. So this T of T is the current temperature, and delta T is the difference between the set and the current temperature. So now for delta T, we substitute here from this expression. So delta T here becomes lambda square minus 1 times T of T, and this is actually substituted here, and then we solve for the scaling factor lambda, and you can see this lambda now has become a function of the time step and the ratio between the set temperature and current temperature, and more importantly the coupling constant called tau. So depending upon the value of tau, the lambda will be adjusted, and so in this approach, what we are trying to do is at every time step we are not scaling simply by this factor, so that in one single time step itself the temperature is reset. We are not doing that, but rather we try to do it in a particular way, or in a particular rate by which slowly the temperature will catch up to T set, and the rate of such an increment is given by this parameter tau, which is called the time constant in the Bunsen thermostat. So now the time constant tau is very important because it tells how quickly we are able to set the temperature to reset to T set. So when tau is very large, that means we are having very long time, we are allowing the system to take long time to reach T set. So the coupling becomes very weak, that means the energy transfer or energy coupling between the system and surrounding is weak, and T reaches T set very slowly. On the other hand, if tau is very small, that means the rate of exchange, heat exchange is very fast, so the coupling is very strong and T will reach T set very quickly. So by this one would think maybe we should take tau to be very small so that the temperature can reach immediately to T set, but that is not correct, because if you couple this temperature too quickly, the same effect that we had in the velocity rescaling method will apply here. That means the sampling of the configurational space or the phase space will not be exactly equal to the constant temperature simulation, so we will be deviating from them. So some optimization is required to find the optimum value of tau. So one of the way one should probably do about this is, whatever measurement that we want to make, you measure that for different values of tau and then see if there is any dependence of the parameter measured with tau. So typically tau is taken to be about 400 to 500 time step. Tau is in the units of time and delta t is a time step used in integration of the equation of motion. So typically tau is taken to be about 400 to 500 times the time step. So that is a rule of thumb, but one should actually measure the property of interest as a function of different tau values and see the sensitivity analysis and then choose accordingly. Now this another thermostat which is very commonly used are known as the stochastic methods, and one such example is known as Anderson thermostat. So in this Anderson thermostat, what we are trying to do is, again we try to couple the system with surrounding, but in this case instead of a deterministic process like Bunsen thermostat, so here the coupling is stochastic or it happens in a randomized fashion. So here also we think about that the system is coupled to an external heat bath which is kept at T set. Now the coupling here is represented by some stochastic impulsive collisions that occurs occasionally on randomly selected particles. Now these stochastic collisions with a heat bath is like a MC move that moves the system from one energy state to another energy state. So you might recall that we were talking about this constant temperature simulation being in the phase space, that energy the system basically jumps from one energy state to another energy state and then vice versa. So now this stochastic collision of the systems with the surrounding basically encodes this kind of energy transitions. So every time the system takes some energy from the surrounding, it basically means the system is jumping some energy level. Similarly, when it gives off the heat or when it cools down, then it means that we are actually going from high energy state to low energy state. So we make many such transitions, except that these transitions are considered as a stochastic event. Now between those stochastic collisions, we look at the system as if it is a constant energy system. So whenever the energy is exchanged with the surrounding, only then the energy changes, otherwise the system behaves like a constant energy system. So with this we will try to implement this algorithm. So in this case also the strength of coupling between the system and surrounding is given by certain rate known as the frequency of stochastic collisions nu. So this is a parameter which resembles that of the coupling constant that we used in Bunsen thermostat, which was tau. So now if you look at these successive collisions are uncorrelated, then the time interval between subsequent collisions seem to follow a Poisson random variable, and the Poisson random variable is given by this exponential function nu times e power minus nu t. So what this means is, this probability p of dt is basically the probability that the next collision will take place in the interval t to t plus delta t or dt. So this dt is nothing but the time step. So now in this particular algorithm, what we first do is we start with some initial conditions, that is R0 and V0, and then we integrate the equation of motion for a time step delta t. That is the first time step for time step of integration, where the particle position and velocities are updated. And then after this we select a certain number of particles to undergo collision with the heat bath, and the probability of a selected particle to undergo a heat bath is given by nu times delta t. So, nu is a parameter that we have to supply, and delta t is the time step that we have designed. Now, suppose if a particle I is selected to undergo collision, what we do is we erase its velocity, which we obtain from equation of motion, but rather we take the velocity from a Maxwell-Boltzmann distribution corresponding to a set temperature of T set. And then if you continue to do this, one can guarantee that this scheme will generate a canonical distribution of the state trajectory. So we call this as a stochastic method, because that here the coupling between the system and surrounding is not deterministic, but we randomly choose certain particle and then we check over a time period delta t time step whether the given particle can undergo collision with the thermal bath or not. We decide that based on some random number generation. If so, then we delete its current velocity and then we take velocity sampled from a Maxwell distribution and then reassign the velocity. And when you do this over and over, then we find that the velocity distribution follows a Maxwellian distribution, which is a true representation of constant temperature simulation. Now, this also becomes an important parameter which will determine whether the system is sensitive to this kind of a coupling constant. So, if you look at on the left hand side, we are plotting the velocity distribution. You can see that it nicely follows the Maxwell-Boltzmann distribution, and the simulations held with the two different frequency of collisions 0.001 and 0.01, both of them basically re-establishes the expected Maxwell-Boltzmann distribution. On the other hand, if you look at the mean square displacement of particles, you see that there is a dependence, so that the slope basically changes. The slope basically is given by the slope will give you the diffusivity, and you would ideally expect that this diffusivity should be independent of this parameter nu, but in this case you see that the diffusivity that we calculate will be a strong function of the frequency parameter. So, because of this, when you want to look at some transport property or dynamical property, we do not use this Anderson thermostat, or we have to look at specifically such a dependence and then decide. As far as equilibrium properties are concerned, this method works just fine. Now, as the example of the extended system, we will talk about this Nose-Hoover thermostat. So, what we mean by extended system is that so far our way of looking at the temperature coupling between the system and surrounding is to think of only the system, and surrounding is coming only through this stochastic collisions or some sort of heat transfer as a deterministic process. But in the extended system approach, we think of the entire system and the surrounding together as a composite system, because if you consider the system and surrounding put together, you can think of the composite system to be at a constant energy. So, we try to rewrite the Hamiltonian not only as a function of the system's variable. So, you can see this corresponds to the kinetic energy of the system, this corresponds to the potential energy of the system. Apart from that, we also additionally write two additional terms to account for the heat bath also. So, for this we defined an additional kinetic energy type of an additional potential energy type of a term by giving an additional coordinate known as S, and then this Q here is called the effective mass associated with this additional coordinate S. So, what we have done here is we have changed the Hamiltonian of the system itself by having an additional degrees of freedom and the additional effective mass. So, with this equation of motion, we can go to Lagrangian or Hamiltonian mechanics and then rederive the equations of motion, and you see that the equation of motion for the velocity, the rate of change of the particle position remains the same, but in the case of the rate of change of momentum, we get this additional term which is proportional to epsilon times pi, and then this eta here is the rate of change of eta is also given by this equation, and then the rate of change of S is given by eta itself. So, instead of solving only these two equations which we used to do in Hamiltonian mechanics, we are now going to solve simultaneously 4 equations. So, all of them will simultaneously evolve, and then once we solve this, we get the true particle position, and then true particle momenta, and then the time step. These are all now scaled back by the scaling factor S. So, as an user, what you need to do is we have to decide what is this Q parameter, that is the initial mass. So, the initial mass will tell you how strongly the system and the surrounding are coupled, and then we think about the system and surrounding as one composite system, and we write the Hamiltonian. From there we derive the system of equation of motion, and then we simultaneously solve. So, this will lead to an additional computational cost, because apart from these two we also have to solve for the additional 2 degrees of freedom as well. So, now here in this News-Hoover method, we look at the effect of this the mass, the initial mass Q, and on the left hand side if you look at the distribution of velocity, we see that whether Q is 0.1 or 1.0, they both basically have given the same velocity distributions, and the value of Q basically means that when the Q is very small, we think about it having a small inertia or low inertia. It means that the temperature fluctuation will be rapid, and that will lead to a very slow equilibration. On the other hand, when we set Q to be very large, that means we assign that the inertia to be very high. So, then the temperature the response will be very slow whenever the temperature is changed, and in the limit Q tending to infinity, we basically recover NVE, or the constant energy kind of behavior. And you can see that this effect of Q on the temperature jump is given in the second figure, where for over a period of time the temperature is at 1, and then around this point at this particular time step the temperature is reset to 1.5, and then we see for this kind of a step change in the temperature how the system responds as a function of different Q value. So, when you can see that when Q is very small, you can see that it gives a lot more fluctuations compared to larger Q value. And then if you look at this dynamical quantity such as mean square displacement as a function of time, you see that the Q values from 0.001 to 100 over a range of 4 orders of magnitude, the value of mean square displacement did not really change. So, all this method we will have to do this kind of sensitivity analysis if I'm interested in the mean square displacement or GFR or any thermodynamic properties. We have to do this kind of sensitivity analysis to make sure that the system is not being affected by the parameter that we set. So to summarize, in this lecture we looked at some algorithms, methods by which temperature can be maintained constant in the MD simulation. The first method is called constraint methods. One example of such constraint method is velocity rescaling. In this case, in this velocity rescaling, at every time step we look at the kinetic energy, and then we calculate the instantaneous temperature, and the instantaneous temperature is different from the set temperature. We rescale all the velocities by a factor lambda, which is given by square root of the set temperature divided by the instantaneous temperature. So, this leads to an isokinetic MD simulation, and we noted that this isokinetic MD simulation is not truly constant temperature simulation, because in constant temperature simulations the kinetic energy should be allowed to fluctuate, but here by construction we are maintaining kinetic energy is fixed. So, that is going to induce some bias, systematic error. So, that has to be carefully checked. Because of this reason, velocity rescaling is only used during equilibration, so that the system reaches equilibration faster. Once the production run starts, we have to use better methods such as Anderson thermostat or News-Hoover thermostat. Then we talked about a Berenson thermostat, where we, instead of rescaling the temperature in one step to reach T set, we do it gradually, and this rate at which we adjust the temperature is given by a certain parameter tau, which is called a time constant, that tells how strongly the system is coupled with the thermal bath. Then we talked about stochastic method, where the same coupling between the temperature between the system and surrounding is governed by some stochastic collision between the system and surrounding, where we randomly select some particle from the system, based on certain probability, we reassign the velocities from a sample taken from Maxwellian distribution itself. And then there are some extended methods, and there are many variations of extended methods, but one example we saw, which is known as Nusshoover method. The idea behind extended method is that we give additional degrees of freedom to account for the interaction with the surrounding, and then we can also control the strength with which the system and the surrounding is coupled by the parameter q. And there are many other methods like Langevin, Parinello, Rahman thermostats, and etc. But the main principle behind all these methods are either Berenson like or Anderson like or extended systems like Nusshoover. So there are many such thermostats, but most commonly you will see that Nusshoover or Anderson thermostats are being used.